In this video, we're going to look at the proof of the one-way ANOVA formula that the sum of squared differences of each individual observation in the grand mean equals the sum of square differences of each observation within a group and the mean of the group plus the sum of squared differences of the mean of each group and the grand mean. So here are the three things, and so if you look at what's going on with the summations here, this is what you'll see that is going on. So I color coded the total with a blue dot, and really what we're doing here, if you look at this, we're taking every individual observation of every group and we're just relating it to the grand mean. So this line is our grand mean right here, and we are simply taking all the distances of every point in every group, and we're taking those distances and which is a difference. When you see the word difference, think of a distance. And we're squaring them up and we're summing them up then. And so our formula says that these square distances are equal to the sum of squared differences of each observation within a group. So I color coded this red. So what that's talking about is if we take within each group, I did two groups here. Okay. Usually you're going to have three or more with ANOVA. That's kind of the point of ANOVA, is we have with ANOVA you have several populations and you take a sample from each population, you take the means of the samples and compare those, and from that you can do an ANOVA test to judge if the general population means are pretty close to equal. And so this part here, sum of squared, the W stands for within, okay, within each group. So we're going within each group and we're taking each observation, and now we are basically taking the difference between it and its own mean. So that's going to be these squared distances. Okay. And then this plus this equals the total. Well, what is this? Well, here this is between. B stands for, W is within, B stands for between. Within groups, between groups. Within treatment groups, between treatment groups. Well, the between, the way we judge that is we're looking at the mean of each group and comparing it to the grand mean, and that's what's going on here. And so that would be, for each point, it would be just this distance. They're all going to be the same within each group. Okay, so remember, this here is between groups. This is within groups. Okay, so if you look at this, it seems to kind of make sense. Here we have a point and we have the total distance, then we have the within distance, and then we have the between distance comparing the group mean with the grand mean here. And it looks like blue equals red plus green. Blue equals red plus green. But this is a flawed example because, for one thing, we're doing linear distances and these are squared distances. It's more like Pythagorean theorem. And the other flaw is you can't use this graph to prove anything really, because if you look at this point, this looks like green equals blue, red plus blue. And so that's why we need a rigorous proof to show us that even though these both look like they're doing different things, like they have different relationships, overall, your whole experiment, this relationship will hold. I'm going to give an example coming up next where you can just, before we actually do the proof, you can actually experiment with my symbology, which seems to be fairly mainstream, but a lot of books and teachers use different symbols and it can be very confusing. So I want you to get used to the symbols here, the K, the I, the NI, the J, everything here, the grand mean, the individual observations and everything. So that it'll be easier to follow what's going on with the proof. And even though I'm not teaching how to do an ANOVA test right now, the big picture here, just real quickly, you would get your F statistic based on the ratio of this and this. And here it is. You put the between groups ratio on top, and with the within group ratios on the bottom. And from these here, you would get your standard deviations, your population, I shouldn't say standard deviation, your population variances. You would have to divide by degrees of freedom, because just these here, these are all variability. They're not variances. They're looking at spread in a way, but true variance you have to divide by degrees of freedom, as you hopefully know if you've gotten this far in a statistics course all the way to ANOVA. And so if we take the sum of squared differences between, divide it by the degrees of freedom that belong to that, and then same with within groups, and we get this ratio. And then it kind of makes sense if your variance is your kind of your spread of your data. Well, if your spread between groups, that would be, this here and this here, if they're spread out a lot, if this is big, it's going to make the fraction big, and the bigger the number, the more you conclude your means are probably not equal in your population. But of course, if this line right here, if this group mean was more like this and this one was more like this, it's going to make this number smaller, and it would make the fraction smaller. And so the smaller the number, the more it leads to support of the null hypothesis that the means are equal. But that's all I'm going to say about the ANOVA technique. We'll get on with the proof in a minute. Continuing on here, what I did, this still isn't part of the proof, but just to familiarize yourself with the whole scenario here, symbols and everything that's going on, I made up an example of 3 groups. So here's group 1, group 2, group 3. So the groups are horizontal, and I've got 3 observations within this one, 4 within this one, 5 within this, 3 within this one, and there they are. And I've got like a little legend here of all of the symbols, what they mean. And so if you feel the need, sit and study all of the symbols and how they work in here and what's going on, and then if you want, you can actually do the summations. And I went ahead and did these for the one I made up. It took me a while, but I made up a set where everything's integers. The means within each group are integers. The grand mean is an integer. And notice here that it's customary to use ij. So like looking at this one here, think of it as, in general, it would be, getting get my pencil working here. Okay. So the random variable for each of these things, I'm using y. Some textbooks or teachers use x. Doesn't really matter. But I used y because that kind of seemed to be a mainstream thing to do. And then ij. So for this one right here, okay, well, that's it would be 1, and then I is 1, and j is 1. And so we're in group I here. That's the first group. 1, 1, 1. I is 1. Make sure you think of I first. Okay, but then we've got the first observation, second observation, third observation. So each one is a jth observation. And so that's reflected here. Okay, so I indicates what group you're in. and K would be the number of groups. So, you know, group 1, group 2, group 3, and then moving on down, you know, to somewhere down here would be a K, but I'm not going to leave that on there. But you can see the summations here. If you're summing the groups, well, you're going to go from group 1, group 2, it's going to the index is going to increment until you get to the number K, which is the total number of groups that you have. Here K would be 3 because we have 3 groups. And I is simply the size of sample group I. So this is sample group 1, so I is 1, and NI is N1, and we have 3 observations in here. This here is, we have 4 observations in group 2, and so the number in group 2 is 4. And in group 3, the number in group 3 is 3. So the number of elements in each set. What else here? So I think I pretty much covered it. I think you can see what's going on. And then I actually took this set of stuff and did SST, SSW, SSB, and the total should equal the within groups and plus the between groups, and that actually happened. You can see the total and then the within groups and the between groups, and they do equal. And so that's just one of an infinite number of illustrations. It certainly isn't a proof. But if I would suggest, if you're not totally comfortable with the symbology here, that you practice your summations. Normally, of course, you know, you would do your inside. That's your inside summation. So you'd run through one iteration of this, and then your I would increment up to 2, and then you would do this thing again. And then your I would increment up to 3 until you get to the last number, which would be K. What else? So yeah, I would just suggest practicing doing the summations. One little point of confusion could possibly maybe be this. Notice that the between group sums of squared differences, it can be expressed 2 ways. And that's the one where we saw that, remember, you had your so you had like group 1, group 2 mean, and then for however many points, remember it was the same distance. Okay, that is reflected right here. Take a good look at this here. We got rid of the J summation, and it was replaced with NI. Well, if you think about it a little bit, run through it a little bit till you're comfortable, you're going to see all that's going on is if you have a summation of something like that, and you have an expression over here that doesn't even have any i's in it, what does this mean? Well, okay, actually, let's make n a number. Let's say n is 3. Okay, well, what that means is that you're going to do 6, and then now I is 2. So you do it again. And now I is 3. So you do it again. So basically, you're getting 3 times this number. So whenever you have a summation that has an argument that does not increment according to I or J or whatever it is, this is a constant with regard to this summation. So all it does is keep getting summed and summed and summed again and again, but it doesn't change. So if you think about this expression here, well, there's only an I in here. The J is not going to keep incrementing anything in here. So all that's going to happen when you do just this inside part here is you're just going to get n times whatever was going on in here, exactly like we did here. And so I would suggest getting comfortable with going from this form of SSB to this form. so that NI makes sense to you. And then it's actually easier to use this way than it is this way. So I'd recommend, take this, go ahead and do your J summation, which is what this is. The J summation was already done. It was taken care of by simply taking this number and multiplying it by the argument here. And then, of course, we can't do that with the other summation because this does have i's, and so now these are going to increment. If you would like a generalization, since this is a specific set, if you want, really proofy looking type things, and you want it as general as possible, basically this would be a generalization of this specific example. So, you can use this if you want, look it over, study it kind of, if you want, or not. So now let's go ahead and do the proof. Okay, you've been wondering when I'm finally going to get to the proof. Well, we're finally there. So the first thing we're going to talk about is the key to the proof, because basically this expression here is what does the proof for us. Once you get this, the proof's going to be easy. Basically, this expression here is equal to 0. That's what I want you to see, because we're going to see that in the proof later, and we'll know exactly what to do at that point. So let's think about what's going on here. So this only has the J summation. We know that there's an I summation too that comes into play, but what we're going to see is whether we're on this I or this I or this I, it doesn't matter. The same thing's going to happen. This is still always going to equal 0. So I is irrelevant right now. So you probably know when you have a summation of 2 or more terms, well, you can basically distribute the summation in front of each term. You're not doing multiplicative distribution, but it kind of looks like it is, but it's not, obviously. But you can distribute summation. So all I did was take this and put one in front of this and one in front of this. So that's the only difference between this and this. Okay, well, let's think about what is this? So since I is irrelevant, just to illustrate this, let's pick an I. So let's say we're on I 1. So if I is 1, that means we're in this group here. Okay, we could have done the same thing if I was 2 or I was 3, but so let's just pretend we're on this group right here. Okay, and then J is 1. So J is 1, that gives us this. And then if J is 2, we're going to add this. If J is 3, we're going to add that. So all we're doing, all this is the sum of terms in the ith group. Okay, and then what is this? Well, we're subtracting, and remember what we saw before, that I have an argument here that does not increment according to J. So this is simply going to be this. It just means this thing is going to happen n times. Okay, well, so this is the number of items in the group, which there are 3 here, 3 times the group mean. Well, that's 5. Well, this is 15 minus 15. Okay, and we could have done it with this group or with this group, and we'd still keep getting 0. Okay, so starting here again, we distribute the summation symbol in front of each term, and then all I did to get from here to a rigorous proof of that this is truly equal to 0 is I just did some fancy manipulation here. I just took this thing here and divided it by ni and also multiplied it by ni. So I'm just multiplying this thing by 1. I haven't changed anything. If you divide something by a number and also multiply it by a number, you have not changed anything. You've only changed the look. So that's what we've got here. So multiplied by ni, divided by ni. But now, what is this part? Well, we saw that the top part, the numerator, is the sum of the terms, and the bottom is the number of terms. That's just going to be the average. That's just going to be this thing. So, so over here, so let me make the equals red so it's easier to follow with the eye here. Okay, so we've got these two terms, which are these two terms here. This term we saw it just turned into Ni times the mean of the group. And then we already knew that this thing was this thing, which is this thing. And so we end up seeing that we have an expression minus the same expression, and that gives us 0. So we will see in the course of the proof this expression, and when we take it to 0, it will make the proof happen. Okay, now we're going to do the heart of the proof. So I went ahead and put the key to our proof up here in blue, and this is just a summary of all three of our terms that we're dealing with. We want to show that this equals this plus this. These three summations, I didn't put the i's and j's and the k and the ni in there, but just consider that they're there. Okay, so we start with SST, and we want to show that that equals SSW plus SSB. So we're going to take this and just start manipulating it. So what I'm going to do now is just take this thing here, and I'm going to use a square bracket. And what I'm going to do before I write this thing, I'm going to subtract make that a little bigger. I'm going to subtract a group mean, a miscellaneous group mean, and add it back immediately so that I haven't really changed anything. So this is really just this. And then just so we can kind of visualize the way that, we'll kind of make more sense, even though the parentheses aren't doing anything yet, but I'm just grouping them. And now we're just going to FOIL this. Think of the parenthesis. This parenthesis is one thing, this parenthesis is one thing, and if we thought of this as this parenthesis is A and this parenthesis is B, and we're squaring that. So if you had A plus B squared, and you FOILed A plus B times A plus B, you would get A squared plus 2AB plus B squared. And so that's what we're going to end up doing with this. We're just going to square this whole thing. So when we FOIL this, this is what we get. So we get the first thing squared, and then we get 2 times this thing times this thing. And then we get this thing squared. Okay, and now we're going to first sum over j. So I'm just going to ignore this, but this j summation is going to get distributed to all three of our terms, and we know we can do that just from properties of summations. Okay, so I'm splitting up the summations, and just the J1 is going to go inside for now. So we're summing over J, and so we're going to get, so this is going to be left just like it is. Okay, and then this one, I'm going to take the J summation and I'm going to put it in front of just the part that is pertinent to the J summation. This doesn't have a J, and obviously the 2 doesn't have a J. So they're constants with regard to the J summation. So we can put those in front. And then we're going to put the J summation in front of just the part that it's actually going to increment. Okay, so I took the J summation and I distribute it to this term, and then the last term. And actually, at the same time, we've already seen that when I sum this thing over J, which doesn't have a J in it, then we can actually turn that into this. Okay, so we can consider this expression having been summed over J, and the I is still waiting. Now we are just about done, because this right here is this thing. And we've already seen that it equals 0. And if this is 0 and this is a constant with regard to this summation, then this constant is going to get wiped out by this 0, and this entire thing goes away. So now we're going to move down a little more, and now we sum over I. And so for this, I'm just going to stick it inside here, and we're just going to get this. This is now gone, and so the only thing left is this. So I'm just going to put the I summation in front of this thing. And this thing here is the sum of squares within. This is the sum of squares between. And we have proven that SST is equal to SSW plus SSB.